Hello, today we're doing 1.4a, continuity and one-sided limits. So in mathematics, the term continuous has the same meaning as in everyday usage. So like when we talk about something continuous, it means it doesn't stop. So it says the function f is continuous at x equals c. It means that there's no interruption in the graph at x equals c. There's no interruption. So, and by that it means that there's no holes in the graph, there's no jumps, there's no gaps. These pictures identify three values where the graph is not continuous. At all other points in the interval, the graph is uninterrupted and continuous. And so see right here, this is a hole in the graph. That is not continuous. Here we have a jump in our graph. We're up at a certain point and we jump down or jump up. That is not continuous. And here we have a gap, also not continuous. And so we know this because here it's not even defined at that point. We would have to pick up in general, if you have to pick up your pencil to draw the graph at some point, it's not continuous. There's not even a value for c. Here the limit does not exist because we're going in two different directions, so that can't be continuous. And here we have that gap. The limit of the function doesn't actually equal the point there. And so therefore it would not be continuous. So continuity can be destroyed, meaning we don't have continuity if the function is not defined, at x equals c, like there's not even a point there. The limit of f of x does not exist at x equals c. So if the limit does not exist, we know it's not continuous. Or the limit of f of x exists at x equals c, but it is not equal to f of c. So these three things would destroy continuity. So the formal definition of continuity is the opposite. The function is continuous when f of c is defined, the point is there, the limit exists there, and the limit equals the point. So a function is continuous on an open interval when the function is continuous at each point on the interval. A function that is continuous on the real line is everywhere continuous. So if the point and the limit are equal, it would be continuous. Like if this was filled in, it would be a continuous function. So now we're going to look at describing the continuity of each function. Is it continuous? Well, let's decide. 1 over x. So what's the domain of 1 over x? It would be anything except that at x equals 0, right? X can't equal 0 for the domain. And so we know that this isn't going to be perfectly continuous, right? At x equals 0, we have a a non-removable discontinuity. So at x equals 0 is a non-removable discontinuity, and we'll talk about what that means in a second. And what that means is, let's go ahead and pull up the graph. If you pull out your calculator, y equals 1 over x. What's happening at 0? It's a non-removable discontinuity because it's not just a little hole in the graph that we could fill in. It's not like a removable discontinuity. It's not just a little hole. It's actually that like the limit doesn't exist there. So it's non-removable. And so there's no way to define it to make it continuous there. For b, we have the domain as all real numbers. We could factor this and we would know that at the bottom, we cannot have x equaling 1 for our domain, right? That would be discontinuous. However, at x equals 1, it is a removable discontinuity. So let's look at what that means, and I'll show you how to be able to tell every time. So let's graph it. Y equals x squared minus 1 over x minus 1. So we graph this guy. And we see that it almost looks continuous on the graph. But if we get to 1, that point doesn't exist there. So it's actually a removable discontinuity. It's just a hole. And the way that we know that is like we could cancel those out. If you can cancel it out at that point, it's a removable discontinuity. It's going to just be a little hole. Okay, let's look at C. The domain of H is all real numbers. We hit all of them at some point. And so we'll have to see if it's continuous. We know it's continuous here because that's a line, and it's continuous here, it's a parabola. But what about where they meet? At 0, we would be at 1 for the first equation. At 0, we would also be at 1 for the second equation. So we know that this is continuous because this is doing its own thing and this is doing its own thing, but where they meet, they're the same. So we never have to pick up our pencil. It's a continuous function. What about D? Sine of x. We know it looks something like that. That's continuous. It doesn't have any gaps. It doesn't have any breaks. No need to pick up our pencil. Okay, this is really important. One-sided limits. So a one-sided limit is telling us that we are evaluating a limit from the right or from the left. So it's the same notation except we have a little plus sign if we're coming from the right and a little minus sign if we're coming from the left. And so what that means is we are just looking at the limit from the left or from the right. So this one says find the limit of the square root of 4 minus x squared as it approaches negative 2 from the right. So that would be the limit as x goes to negative 2 from the right. So it would have a little plus sign saying from the right of 4 minus x squared. So we're looking at it here. From the right, from negative 2, as we approach it, it would be 0. And that would still be the same thing from the left too, right? And the limit. Sometimes they all equal each other, yet sometimes they don't, like this one. Find the limit of the greatest integer function as it approaches 0 from the left. So let's look at the limit as x goes to 0 from the left and the limit as x goes to 0 from the right. Well, let's look. As x goes to 0 from the left, our limit is down here at negative 1. Because as we're coming from the left side, we're here. As it goes to 0 from the right, we're actually at 0. Does the limit exist at x equals 0? It doesn't, but from the left, it's at negative 1, and from the right, it's at 0. So we would have to say the limit as x goes to 0 does not exist because the limit as x goes to 0 from the left does not equal the limit as x goes to 0 from the right. They don't equal each other, so therefore the limit does not exist. Okay, one more continuity one to get into. A limit, so just real quick though, the limit only exists if the limit is the same from the left and the right. Then you would know that that's the true limit. If it's the same from the left and the right and the limit are all the same, then we know that it is continuous and it has the limit. Okay, discuss the continuity of the square root of 1 minus x squared. So we're going to think about this fact that we just talked about. A function is continuous if the limit from the right equals the actual point and the limit from the left equals the actual point. Then we know that it's going to be continuous because they're going to equal each other. Okay, so we have a function here. We have the square root of 1 minus x squared. We know that our domain would have to be from negative 1 to 1 to keep this positive under our square root. We know that this one would actually be continuous because the limit as x goes to 1 from the right is 0, which is that point there. And the limit as x goes to 1 from the left is also 0, which is the point, of f of 1. So see, these are backwards. So it says the limit as x goes to a from the left, does that equal f of a? And the limit as x goes to b from b, does that equal the point? So basically, as long as your limit actually equals your point, then we know that we are continuous. And this one, you can look at the picture as well. All right, thanks for watching.